The planet Mars is a red, cold desert, incapable of supporting life. But can you imagine that one day we will turn it into a blue and green world full of rivers, oceans, forests, and breathable skies like those of Earth? How would we achieve this? How long would it take? What technologies would be needed to turn a dead planet into a new home for humanity? In this chapter, I'll take you step by step on a journey to see the most ambitious undertaking humanity could ever conceive: the terraforming of Mars. With real science, we could completely transform an entire planet and make it habitable. Step 1. Magnetic field. Before we begin any attempt to terraform Mars, there is a fundamental problem we must solve: its complete exposure to solar and cosmic radiation. Mars lost its magnetic field about 4.2 billion years ago. Since then, it has been vulnerable to the solar wind, which has not only stripped its atmosphere for eons, but also sublimated water, preventing life from forming on the surface and, over the long term, deteriorating any structures. Without a magnetic field, there can be no water, no air, and no life. So if we want Mars to be habitable, the first logical step is not to warm the planet or bring in water. It is to restore its shield. But how could we do something like that? Although it may sound impossible, this is one of the quickest and easiest problems to solve. In fact, there are serious proposals about this. One of them was made in 2017 by Dr. Jim Green, NASA's chief scientist. Green's idea is bold in its simplicity, as it involves installing an artificial magnetic shield at the Lagrange 1 L1 point of Mars, a gravitationally stable region between the Sun and Mars, about 650,000 miles from the red planet. From there, a sufficiently powerful electromagnetic structure could generate an artificial magnetic field that deflects the solar wind, just as Earth's magnetic field does. The brilliant thing about this proposal is that it would not be necessary to build an artifact that surrounds Mars, since it would be enough to place it between Mars and the Sun, serving as a shield. The technology for this does not yet exist on a planetary scale, but its foundations are well understood. It would be a combination of giant satellites with dipole field generators, possibly powered by nuclear or fusion reactors. To get an idea of the scale of the project, a field of about 1 to 2 Tesla strength would be needed to effectively deflect solar particles, which is technologically feasible, but would require colossal space infrastructure. And how long would it take to build this shield? According to Dr. Green's estimates and extrapolations made by planetary engineers, the full deployment of a functional network could take between 50 and 70 years, depending on advances in nuclear propulsion, space mining, and automated manufacturing in orbit. This would include the modular construction of the satellites, their stable positioning, and the controlled activation of the field. The effects, however, would be almost immediately at the planetary level. Once the shield is active, Mars would be protected from ultraviolet radiation and cosmic rays. This shield would be the first step toward Mars becoming less exposed and transitioning to a living planet. From here, the complete transformation of the red planet would be officially underway. The next step in making Mars habitable is temperature. Enjoy deep, fact-checked space stories? Hit subscribe and activate the notification bell. Otherwise, YouTube will not show you the next videos and you'll miss what we uncover next. Step 2. Temperature. Mars is a cold planet, extremely cold. Its average temperature is around -80 degrees Fahrenheit, and on Martian nights, it can drop to -195 degrees Fahrenheit. Even with a magnetic shield, no human could survive those temperatures. If we want to make Mars habitable, the next step is simple to understand, but titanic in execution: raising its temperature. One of the most supported proposals by the scientific community is to create a controlled greenhouse effect. This wouldn't mean polluting the planet, but releasing gases with high warming potential, like carbon dioxide, CO2, water vapor, and especially perfluorocarbons, PFCs, into its atmosphere. PFCs are over 10,000 times more efficient than CO2 at trapping heat, but they don't occur naturally on Mars. To produce them, we'd need robotic factories powered by solar or nuclear energy working for decades on the Martian surface. CO2, however, is already present on Mars, locked in its polar ice caps and soil.
But recent studies show there's not enough accessible CO2 at the surface to warm the planet sufficiently on its own. So this method alone wouldn't be enough. That's where a bolder but feasible alternative comes in: bombarding Mars with asteroids rich in CO2. The idea is to redirect icy bodies from the asteroid belt, select those loaded with CO2, and impact them on the planet's surface. These collisions would release gases into the atmosphere and generate local heat, melting underground ice. Do we have the technology for this? Yes. On November 24, 2021, NASA's DART mission successfully altered the orbit of the asteroid Dimorphos by impacting it with a probe, a historic proof that redirecting asteroids is within our reach. If we take this technology to a planetary scale, Mars could be bombarded with thousands of minor, targeted asteroids to gradually warm the planet. According to studies like Robert Zubrin's, founder of the Mars Society, if we combine this with PFC-producing factories and CO2 release from the poles, we could start seeing significant warming within about 100 years. Raising Mars's global average temperature above the freezing point of water might take 150 years, and reaching a temperature comfortable for humans could take up to 200 years. After stopping the asteroid bombardment, we would need time for the dust to settle and the skies to clear. That would be the moment Mars would cease to be a cold, red desert and begin to resemble a warm, living world. Only then could the next critical step begin: bringing the water. Step 3. Water. Millions of years ago, Mars had rivers, lakes, and even seas. Today, all of that has vanished, at least from the surface. Yet, modern studies reveal that Mars still harbors vast reserves of frozen water. Some of it lies in the polar ice caps, but significant amounts are also trapped underground, especially in mid-latitudes and ancient riverbeds. One estimate, published by NASA and led by scientist Roberto Orosei, suggests that if all known surface ice were melted, it could cover the entire planet with a 66-foot deep layer of water. That's a staggering amount, but it's frozen. So once the Martian temperature surpasses 32 degrees Fahrenheit, the next logical step is to release that water. One strategy would involve using concentrated solar energy or nuclear reactors to heat targeted ice-rich regions and cause controlled melting. Explosions under the permafrost could also help release vapor, and as atmospheric pressure increases, water will stop sublimating and remain liquid longer. However, even with all this ice, Mars may still lack enough water to sustain large oceans in the long term. That's why the second part of the plan is more ambitious: importing water from space. The best sources are nearby. The asteroid belt between Mars and Jupiter holds millions of bodies rich in water ice. Ceres, the largest object in that region, has a crust filled with ice and possibly underground oceans, making it an ideal candidate for extraction and transport. Redirecting these low-mass bodies to Mars would allow us to release water directly into its growing atmosphere, either via controlled impact or orbital dispersion. We could also take advantage of comets passing near Mars, redirecting them to crash in a safe, controlled way. These would not only contribute water, but also deliver other volatile elements essential to organic chemistry, aiding the future formation of a Martian biosphere. While this idea sounds like science fiction, it's closer to science fact. NASA's DART mission successfully altered an asteroid's orbit, proving we can manipulate small celestial bodies. Future missions could use similar tech to guide icy bodies a few dozen meters wide to Mars safely. This entire process would unfold over centuries. Melting Martian ice could begin alongside global warming and take around 100 to 150 years. Meanwhile, importing water could extend the timeline by another 150 to 300 years. In total, filling Mars with rivers, lakes, and perhaps inland seas might take up to 3 centuries. When this process is complete, Mars won't be red, it will be blue, and it will rain water on another world for the first time in billions of years. At this point, Mars would not yet be habitable, but it would no longer be as hostile to life. Once Mars has a warm temperature and abundant liquid water on its surface, are ready to take your first breath. Step 4. Air. Once Mars has a magnetic field,
a stable temperature, and liquid water, the next challenge is more delicate and prolonged, creating an atmosphere that humans and animals can breathe without spacesuits. Currently, the Martian atmosphere is composed of 95% carbon dioxide, with barely any oxygen or nitrogen. Moreover, its atmospheric pressure is only 0.6% that of Earth. Breathing there is physically impossible. This phase involves two monumental tasks: thickening the atmosphere and oxygenating it. To achieve both, we'll need to combine synthetic biology with large-scale technological systems. The most natural, though slow method would be to introduce photosynthetic organisms such as algae, cyanobacteria, and genetically engineered extremophile microbes. These would be adapted to Mars's new environment, warm, dry, but rich in CO2 and water. Their purpose would be to absorb carbon dioxide and release oxygen, slowly enriching the atmosphere. On Earth, photosynthetic organisms transformed the planet during the so-called Great Oxygenation Event 2.4 billion years ago. A similar process could be repeated on Mars, but on a planetary scale, and with human intervention to accelerate it. In the early stages, these organisms would grow in vast automated greenhouses, biofactories powered by solar or nuclear energy and supplied with water imported from asteroids and comets. As Mars becomes warmer and wetter, they would be released into natural environments like lakes and soils, where they'd begin to transform the planet openly. But even with ideal conditions, this biological process would be painfully slow. According to models developed by NASA astrobiologist Chris McKay, producing breathable oxygen levels through photosynthesis alone could take 10,000 to 100,000 years, depending on the scale of deployment and environmental factors. To accelerate this process, we would need technology. One proposal involves installing catalytic towers that extract oxygen from CO2 directly, powered by solar or nuclear energy. This isn't theoretical. NASA's MOXIE aboard the Perseverance rover already succeeded in doing this, albeit in small quantities. If we scaled MOXIE up to thousands of city-sized reactors distributed across the planet, we could dramatically reduce the time needed to oxygenate the atmosphere. Combined with biological processes, this hybrid strategy could achieve breathable air in about 500 years. It would still take a long time, but not thousands of years. But oxygen isn't enough. We'd also add nitrogen, which is crucial for regulating atmospheric pressure and temperature. This could be done by importing ammonia-rich materials from comets or synthesizing nitrogen directly from Martian minerals using advanced reactors. This combination of technologies would enable the accelerated construction of a stable, breathable atmosphere that prepares the planet for its last great transformation: life. 5. Life. After centuries of planetary work, Mars would finally have the basic conditions necessary to host complex life: a magnetic field, a stable temperature, abundant liquid water, and an atmosphere rich in oxygen and nitrogen. But it is not enough for the planet to be habitable. We need him to be alive. To do this, the next step would be to populate Mars with organisms capable of building entire ecosystems, just as happened on Earth for hundreds of millions of years, but this time in a fraction of that time. The process would begin with the introduction of extremophile microorganisms designed to colonize nutrient-poor soils and transform them into biologically active environments. These microbes, similar to those that inhabit the most extreme environments on Earth, such as underwater volcanoes or frozen deserts, would fulfill vital functions: fixing nitrogen in the soil, breaking down minerals, releasing phosphorus, and forming humus. That is, they would begin to generate fertile Martian soil. Once a microbial base was established, pioneer plants would be introduced, selected for their high resistance, rapid growth, and low nutrient requirement. Mosses, lichens, and ferns, they would be the first candidates, along with species genetically modified to resist the conditions of Mars. These plants would begin to absorb carbon dioxide, release additional oxygen, and, most importantly, establish the first simple food chains. Over time, more complex vascular plants, including shrubs, grasses, and eventually trees, could be seeded, consolidating the water and carbon cycle. These plants would increase atmospheric humidity, facilitating the formation of clouds and rainfall, thereby closing a fundamental ecological circle. At the same time, Martian soils would store organic carbon and living matter, continuously enriching the biosphere. At the same time, semi-open habitats or ecological domes would be built, where insects, fungi, small birds, and mammals would be introduced.
These areas would serve as living laboratories to test the adaptation of terrestrial species to Martian gravity. The total colonization of Mars by complex life would be gradual, starting in strategically terraformed regions, such as equatorial valleys and ancient craters, where climate and water availability are most favorable. This biocolonization process could take between 300 and 500 more years, depending on the rate of ecological expansion, the application of genetic engineering to introduced species, and the maintenance of stable atmospheric conditions. At the end of this process, Mars would not only be a habitable planet, it would be a living planet, covered in green plains, blue skies, and life forms that would thrive on a world that was once red and barren. Transforming a dead, cold, dry world into an oasis of life wouldn't be quick, easy, or cheap. But what if there was a place in the solar system that was easier to terraform than Mars? We dedicated a full video where you can learn it. Watch it here.